Puzzle today. I have a little ramp, and the little ramp is wood on the top and it's metal on the bottom, and specifically it's copper. But on top of the wood and on top of the copper there's a sheet of mylar, so the surface that the car rides on is uniform. It's exactly the same at the top and at the bottom. It's exactly the same, but underneath that mylar, and it's a thin sheet, is a layer of wood and a layer of copper. So I take this car and I put it up at the top, I let it roll down the ramp. It goes nice and quickly on the wood, but when it gets to the copper, it slows. It slows when it gets to the copper. Now there's something special about the copper, and there's also something special about the car. The car has a little magnet underneath. It's got nice rolly wheels, but it's got a magnet, and the magnet doesn't rub. It's not low enough to rub. But there's something about the magnet, and there's something about the copper that causes the car to slow down. So here's a question for you. What is it about the copper that causes the braking when the car gets to that point in the track? We'll give you some choices. And what's special about the copper is this. It's an electric conductor. So there's a connection between magnetism, there's a magnet on the bottom of the car, and electricity, there's an electric conductor in the track. And this deep connection between magnetism and electricity is the subject of chapter 25. Let's look at another experiment. So I've got a solenoid right here, and inside the solenoid is a bunch of iron. This is actually welding rod. So I've got iron inside a solenoid. When I put a current through the wire, there's a field inside. It will magnetize the iron, and so there's going to be a huge magnetic field in the iron inside this tube. And on top of the tube, I'm going to put an aluminum ring. And when I turn a current on in the coil, let's watch what happens. Oh yeah. And here's what happens. When I turn on this magnetic field, there's a huge magnetic field inside that tube. And so there's a huge magnetic field that appears all of a sudden inside this aluminum ring. So there's a huge change in the field inside the ring, and it produces an electric current inside the ring. And there's a force between the magnetic field and the currents that causes the ring to jump up. And we can prove that it's the electric properties of the ring that make it do this in this way. I'm going to take another ring, I'm going to put it on top of the ring shooter, I'm going to push the button, and this one has a very different behavior. What's the difference? This one doesn't move at all. And if I take a view at this ring, we can see the difference is this ring has a break in it. So it is not a continuous conductor, and so there isn't any electric current in the ring. Besides that cut, these two rings are exactly the same. So it's the electric current in the ring that causes the dramatic forces that we've seen. And it's the change in field inside the ring that produces the current. We would say that induces the current. And this is the basic topic that starts chapter 25. And we'll take a look at it in more detail in the next segment.